Great. So this presentation is about the art of searching, featuring Lucene Thing 1 and Thing 2. And so we're going to start with a problem. And we'll try to solve the problem. We'll start with a really simple search example and then move on from there and sort of add features as we go along. So the problem is you want to find documents that match a search string, just like you would on Google or any other search engine. And here are the rules to make it simple for ourselves. Each document is a text from a Dr. Seuss book. You can search for any word or phrase that you want, but there are no fielded searches. So you can't say anything like, oh, I want the title to be Hop on Pop. This is just a free text search. And the result is a list of the books that match. So you can assume that we have two books here, and to simplify things, we're just going to say that the only text in these books are the string of text on the left and the string of text on the right, to make our example even simpler. So you've got one fish, two fish, red fish, blue fish. You guys who have kids have probably read these words many, many times. And same thing over here on the right, you've got another phrase. And you'll notice that some of the words are similar between the two books. Okay, so the first thing we want to do is give each book a document ID. Because we're computer people and we don't deal with titles, we're just going to give it a number. So it's 1 and 2. The next thing we're going to do is we're going to avoid a lot of complexity here and just say we're going to ignore all the punctuation, capitalization, and pluralization, which by themselves are chapters and books and lots of technologies around how you do that. We're going to skip over how all that's done for this explanation, and we're going to create an inverted index, which is the opposite of the normal situation when you think about documents or records in a database that have text, and the document is the primary object that you're dealing with. In this case, it's switched. So the terms, the words in the document are switched. And so what we have here is, in document 1, the word 1 only appears in document number 1, but fish appears in document 1 and 2. And we go through the whole list. And for this particular iteration of the inverted index we're building, it's very simple. All we know about the word fish is that it's in document 1 and document 2. We don't know anything else about where it is in those documents, its frequency, or any other details that we'll be building later on. So if you want to do a search for a single word, such as fish, you look it up in the index and you see what documents it's in. These documents are also called postings in the very formal computer science literature. And so here we have fish as document 1 and 2, and to find a single word like that is pretty easy. It's whatever's in the list is what matches. Now, it gets a little more interesting when we want to search for 2 words. And these 2 words that we're going to search for are just 2 separate words. In other words, fish and blue. We want to look up both words in the index and just make sure that the document contains both of those words somewhere in the document. They don't have to be right next to each other. It doesn't really matter. What matters is that they're in the document. So in this case, both of them, because it's fish and blue, have to be there. And so what you do is just do an intersection and find that both of them happen to have document 1, and so that's where they match. They both are in document 1. Fish is in document 1 and 2, but it doesn't matter because blue isn't there. And then OR is basically combining all the terms. It's the union of each term's results, and so we get document 1 and document 2. And so we're doing a union of these 2 lists. Basically, you're eliminating the duplicates, and that's your answer. All right, so that's great. That's a very simple way. It'll solve some problems for you, but we need to add a lot of things to this inverted index to make it usable at all for any real searching purposes. So in the real world, a term can appear in billions of documents. And so the examples I gave, we only had 2 documents we were dealing with here. So you can imagine what happens if a word is in billions of documents. That list gets really, really big for each term. So we have to know for each word what its frequency is. How many documents does it appear in? And we can use that information to actually make the search more efficient. So obviously fish appears in 2 books, but blue is only in 1. This number that fish appears twice is the document frequency of the word fish. And so it appears in 2 documents. So what we need to do to make our searches more efficient is to actually add that number into the index. And what you can do once you've done it, you can see the notation I invented here is you put the frequency colon before the list of the documents. And so in this case, we know that fish has a frequency of 2, and it's either 2 or 1 all throughout here. Okay, so then there's an algorithm to efficiently intersect once you have this. And I won't go through each step here, But if you want to get a list of if you want to do this, you want to start with the term that has the lowest frequency and work up to those that have the biggest, so you're doing the least amount of work. And so the way we do this is you get all the list of the terms, start with the smallest, and then you create a list of the postings for the first term that's in that list, and then you assign t the rest of the terms, and you just go through this loop where as long as t and r are not empty, what you do is you just reassign the result, r being the results, the intersection of the postings, and then t is the rest of the terms, and you just loop until basically you've intersected all the way up. But what you're doing by starting with the smallest group is you're making sure that you're not trying to go through the massive list. If you have one postings list that has 2 elements in it and your other element has a billion, well, very quickly you're down to just dealing with 2 terms instead of cycling through the billion. All you're looking through in those billion terms are the 2 terms that may match what you have in that shorter list. So that's, in a nutshell, what that algorithm does, is it makes it so you don't have to go through the larger list. But we still have a problem. In a large system, there can be an enormous number of documents. So even though we're starting in the correct order and we're going to go and try to do the least work amount possible based on the document frequency of the term, you still could have, and those of us that are on the Clicks team are quite familiar with large data sets, you still can have a situation where you have fish appearing in 6 million documents, which is small in a lot of terms, and the blue word appears in 100. So it could be that we would need to go through over 6 million operations if you had to end up traversing through the whole list to find something. So the way that we can make this better is we change the way that postings lists work. So the way we had displayed it before was basically it's a linked list. So what you do is you create a linked list with skips. And so in this case, you actually skip every 3. And so the algorithm is that you point to the first element in both lists. And what happens here, to just describe in a second what I'll just illustrate here, is you have these 2 pointers and they basically chase each other to see how far they can skip ahead. And when they reach the end of the list, they know they're done. So if you reach the shorter list first, you don't have to traverse the rest. And so the algorithm here is you go and see if you're the larger one of which one is smaller, and then you advance the one that's smaller all the way through, skipping each time and chasing each other, and hopefully skipping over as much of the list as you can. And so we start here with fish 1 and 2, and so there's no match. So what we do is we actually advance the fish 1 element since it's less, and there's no skip pointer for that position, so we just move to here. And so now 2 matches 2, so we add it to the list of the matches and we advance by 1. Then we go here and we advance again both of them. So there's no match. We advance via skip pointer as far as possible without going over 32. So we end up landing here. There's no match, but we don't advance the skip pointer since 45 is, I think my animation is ahead of my text. Since 45 is more than 32, and we advance fish by 1 instead. There's no match, so we advance fish by 1. And there's no match again. And so we simply go here. Now we have a match, and so we add this to the results. And we just go through here step by step using the skips as much as we can to try to avoid looking at each and every element in the list. And so you can see here as we go through, we have a larger list, but what really drives the comparison here is what's in blue. We have a match at 80. We're at 95. There's no match. We know we're at the end of the list here looking at it. We advance until we get greater than the last element in that list. And so now we know we've reached the end of the list. There's nothing more to do. And we return the results. And so you can see there that if you're lucky enough to end before the end of the list, not only do the skip pointers help you, but you eliminate all whatever could be out here, which could be millions of rows, if you happen to just hit that you match at the end and you've exceeded the maximum on the other list. But there's still more that we can do. So what we have started with is we were talking about if we just have AND queries, Boolean queries. But what about if we want to do something like query for a phrase, which everybody does? And so in this case, we want to find all the documents where 2 is right next to fish. So we have to add some additional information into our list here. And in other cases, we may want to find terms that are within a certain number of rules. So maybe we want to find, if burger is within 5 words of McDonald's, this is a document that we're interested in. And so to find phrases, we still use the same inverted index that we had, but now we include some information about each word's position in the document. So this is what it looks like now. You just keep adding numbers to this. So for fish, here's the frequency 2. Document 1, fish appears at its word number 2, word number 4, word number 6, word number 8. And then document 1, it appears at position 11. And so we do that for every word, and now we know where all the words are, and so we can start to see if they're next to each other. So here's a revised intersect algorithm, and you can actually look at the official pseudocode version if you want. I give a reference to a book later, but this is for explanatory purposes basically what's going on. The actual code is slightly different. So you accept as input 2 postings lists, P1 and P2, and a max distance k, which is how many words can they be apart. So if we're looking for 2 fish, it's 1 word apart. K would be 1. And your postings list here, if you were looking for, say, the word 2 and the word fish, you're talking about P1 maybe being the postings list for fish and the other one being postings list for the word 2. You create a list of the answers, which is initialized to empty, and you start at the beginning of each posting list. And if the document IDs match, then you get a list of the positions. And basically, you start at the list of the positions list, compare the absolute value of all the positions in the matching documents, and see if they're within K. If they are, they become part of the answer. If they're not, you move on. And then after you've gone through and found you had a match in a document, then you need to, and you've exhausted all the list of the positions that match, then you move on to the next set of documents that match. So it's basically the same algorithm before where you're cycling through and chasing which documents are there, but once you get to individual documents that match, then you cycle through each of the positions and try to see if they match as well. So that in a nutshell is what that means. And if you look at the pseudocode for this, it's a bear to read. So this is not going to be as technically accurate as the Manning book, but that's basically what's going on. So that's great. Now we have phrase queries and we have positions. And so we're adding more and more features to this inverted index. Well, one of the things we can do now that we have positions is we can start to look at ranking documents. And so the question is, how do we determine which documents are most relevant to a query? And also, there's a related question that is, how do you determine which 2 documents are close or similar to each other? But let's first focus on relevance to a query. To give a score, in other words, which results should appear first in your results list? And so you have to assign a weight for each term in a particular document, and there's an easy way to let the weight for a term to do this. And what you can do is let the frequency in the document, called the term frequency, be that weight. So in other words, fish appears 6 times in this document 1. So its weight would be fish. That's the importance of fish in document 1. It's it's most of the word. It's the most frequent word in there. And then fish appears 1 time in document 2. But there's a problem with term frequency, which is that every term in a document isn't necessarily important for determining relevance. So some very frequent terms like is, the, have, much, and more can throw off the results. And yet it's true you can eliminate stop words and things like that, but they'll still be common words. So for instance, if you're looking at Scott Liebernight's collection of things he dislikes, the word Java is going to appear there like 1,000 times. So in terms of having any discriminatory power on your search, it doesn't really matter because the word is so prevalent in all the documents, it doesn't really help you find things. So there's this notion of collection frequency, which is the number of times a particular term appears in all the documents in a collection. And you can actually use this to attenuate the effects of these common words. So document frequency is actually a different term, and that's usually used because there's a problem with collection frequency too. So a word that appears once in every one, 95% of your documents, this one word appears. Well, this is a word that is prevalent in the documents, but is it really significant? It's in every document, so does it really have any discriminatory power for your search? Well, it doesn't really. And so that could actually throw off your results because you could have a higher collection frequency if you look at all your documents than the word that appears in 25%. Obviously, if there's a word that only appears in 25% of your documents, sort of common sense tells you, well, probably those documents are related, or at least there's a greater chance that they're related to a particular topic versus something that's just in every topic that you might be covering in your article. So the Search Geek said, I don't know if you guys have ever seen that. There's a Think Geek t-shirt that says something like, God said, and then it has like all these pages of math that apparently explain how photons work, and it says at the bottom, and then there was light. And it's, you can order the t-shirt at thinkgeek.com, I believe. So the Search Geek said this, IDFT equals log of n divided by DFT, And then there wasn't light, but there is this thing called an inverse document frequency, which is really, really useful in what we're doing. What it does is it takes some of the things that the document collection and the collection frequency and document frequency do, and it combines it in a really interesting way. What it lets us do is something that we need to define another thing for to get to. Let me go back and explain here. So basically the idea is if you've got n being the total number of documents, you look at the frequency of a term within the document and divide the total number of documents by that and the log of it, and what you're basically getting is a number that's usually like between 1 and 3 that gives you an idea of the inverse frequency. So there's another thing that we use to get the really good measure of relevance in a document, and what it's called is term frequency inverse document frequency, or TF-IDF, and that it's just dash, it's not a minus sign, it's just all the literature seems to refer to it as a dash, and this is what they call it. And so the idea here is the weight for a term is highest when the term occurs many times within a small number of documents. This kind of makes sense. So if you have an article about baseball, and the word home run and hit and bunt, appear a lot of times in the article, if you have a series of documents, they're kind of a unique set. And so that's what that's trying to capture. And then the weight is lower when a term occurs fewer times in a document or occurs in many documents, sort of attenuating that idea of the collection frequency. And then the weight is lowest when the term occurs in virtually all documents. So the formula is basically taking the IDF times the term frequency for each term in each document. That's the T comma D there. I know that sounds like a lot of mumbo jumbo, but hopefully it'll at least the application of this will be clear. So now that we have weights for each term in a document using this measure, we can actually view the document as consisting of vectors. There's one vector for each term with a magnitude equaling its weight being defined as that formula I just presented on the previous slide. So to determine a relevance of a document to a free text non-phrasal query, what we do is we compute that for each term in the query and we just add it up, and the higher the number, the more relevant the document is. That's cool. That'll help you find documents. But what we're going to do to sort of illustrate this is something I thought was really neat, and it comes actually as part of an add-in for Lucene that you can do. We turn the documents into vectors in a vector space, and you can visualize this by picturing each vector being on its own axis, and then you compare this using a thing called cosine similarity. And we'll probably live through these slides, I hope. So pretend our document is hello, hello, goodbye. So there are only two terms in it, hello and goodbye. And we can kind of picture, the vector here being like the hello vector, and this would be the goodbye, and obviously the hello would have a magnitude of 2, and goodbye would have a magnitude of 1. But most documents don't have just 2 words in it. So if you picture, if it had 3 words, hello and goodbye, you could picture, an extra axis, and so on and so forth. So obviously, a typical document may have 400 different kind of words, 400 unique terms in it, so you essentially have 400 different axes in this vector space. So what we can do is we can try to compare documents then, since we have this set of vectors that represents what's in the document, what the weights of the terms are within the document. We could try to compare the magnitude of the vector differences between them. That's sort of one brute way to do it. However, the thing is that the document length is going to throw this off. So if you have a document that has nothing but the word dog 1,000 times, and then you have another word that has dog once, well, obviously, those are probably related to the same subject, which being dogs, but they would be different using that method because the 1,000 would give so much weight to it, it wouldn't work. So what you have to do is you actually factor in the document length. You're essentially dividing out the fact that that dog is there 1,000 times, and so then you have 1-to-1, and you can actually do a fair comparison. So the standard way to do this is something called cosine similarity, which has a formula, and basically you take the vectors for each of the documents, and you divide it by their magnitude, and what you get is a measure that's essentially the unit vector for each of the terms, and then you can use that to do comparison. So you can kind of picture it like this, where you might be doing a search for jealous and gossip are the 2 terms that you're searching for, and so combining, and so you have a unit vector for document 1 that kind of pushes you here, a unit vector for document 2 that pushes you here, And what you do is you measure and the overall, if you take gossip and jealous, and you figure out what its vector is by combining those vectors. The vector for the search query is here. And so what you do is you basically compare the distance between the query vector and the document. So obviously the distance between the query and document 1 is larger than the query and document 2. So that's basically how you do it. It creates an angle, and you're just looking at the difference between the angle. So it's a really neat technique to basically turn, words into math that can be visualized. That's the sort of the theory behind it. Now, what's neat about it is the practical implementation that we often use in our projects is Lucene, and all of that stuff that sounds like a bunch of rigmarole of math is actually in Lucene doing that for us. So it's nice that Lucene makes it very easy. I don't know if you caught the head fake, but searching really is an art. It's much more of a science. It's much more mathematical. But Apache Lucene gives us something that's very useful. So what I want to do is show you a quick demo of, let's see if it is up. Oops. All right, so the resolution sometimes can make this hard to see. So we started here using the same example. So I actually used the exact same text we used in the example on the slides, a really short document 1 and another really short document 2. And then I used Lucene's indexer to actually go and create an index for that. Let's see if I can make that bigger. I think when Gray and I went over this, hopefully it's, whoops. Hopefully those will be able to be read. And I'm not going to read every line of code, but I'll sort of explain the practicalities of this. So the first line you see is an analyzer. There's a standard analyzer. And what that does is that's the part of Lucene that's going to go and look at the text, but it's going to do things like remove plural words and normalize them to, instead of dogs, it'll make it dog. It's going to do things like normalize email addresses, phone numbers. It's actually a pretty sophisticated analyzer, and that's the part I said we're sort of skipping over all the technical stuff that goes into that. It's very interesting, but all you have to do is create a new one of those, and Lucene takes care of all that for you. We're going to create a new index writer is what all the setup code is doing. And then we will use that index writer to actually write an index, which Lucene will then end up creating multiple files. And so I go through the document directory, which only has those 2 documents in it, basically read them all in. And then for each document, I create a document object, and I take the document to index, and I add a new field to it called content, which by default is the field that Lucene is dealing with when it's indexing everything. And then basically I just take the buffer to string. In other words, I just take the whole document as one big string. I actually store the entire field, so it's possible in Lucene to index an entire document but not actually store it in total as it is in order, in the correct, as you would actually read it. You're just storing the terms individually. So I'm saying we want to store the actual document so you could read it. The idea being as you get results back, you may want to display that. And then what we're asking here is, are we analyzing the field? And we are analyzing the field. And are we generating the term vector? Again, that was the magic with the cosine similarity and all that. And are we generating it with position so you could do phrase queries on it? So that's what that is all about. And then basically you just go through and add the document, index it, and close it, and you're done. And I can run it here. And it's done. I don't think it prints out, well, if it prints out something, it's scrolled past already. And so then we can go and actually examine that index. There's a tool called Luke, and it's part of it's this Lucene index toolbox. And you can just go through and see some of the things we were talking about in theory that you would do in terms of having indices and term frequency and so on. So if we actually open the Lucene index, say, okay, please go and open this. So then we can actually go through and look. So in the content, we have 13 unique terms. Here's a list of what they are, what their rank is in terms of which ones appear most frequently. So fish is the most popular. What field they're a part of, we skipped over the whole field notion. Lucene provides these ways of actually having separate fields that you separately index, so we're just going to deal with the main field called content. Let's see here. We can go into the documents. You can actually browse by document number. So you can go and say, you know, here's the document, here's the whole thing. Let's see if there's anything to. You can do the term vector by clicking TV. And it'll actually tell you sort of the same thing you saw on the slides, where it's here's the term, here's its frequency, here its positions, all the theory that was there. This is actually doing those things in real life. Let's see. You can show the whole thing in the field. And you know, you can cycle through each of these and look. It also has the ability to enter a search expression here. So you could say like fish and 2, something like that. And let's see here. And it'll actually tell you, it'll give you a score for each document, so you can actually execute queries for this tool and see how this index is working. So that's pretty neat. So the terms, Lucene generates an enormous number of files, and they correspond to some of the things we talked about. So there's a term dictionary. Basically, it stores all the terms alphabetically in the TIS file along with their document frequency. And there's another one called TII, which is just designed for memory. So fish is in 10 documents. That's what it means. Term frequencies for each document are in the freq file. And so in document 1, fish appears 6 times. That's basically what that document's saying. Term positions, PRX, lists the position of each term within a document. So in document 1, fish is at 6, 7, 8. And then you have term vectors, which basically stores a lot of that information combined. But what it acts like is for each document, because Lucene has this ability to not just deal with the content field, but also have multiple fields in there that are unique, it actually provides like a mini inverted index within each of the term sets for a particular document. All right, I think we're close to the last slide here. So actually, as most of you know, we actually have a poster about it over there. Aaron McCurry has created a open source project called Blur that uses Lucene. I think folks that have seen this have been really amazed by what was done here. Blur is basically sharded Lucene, and it spreads its index over an entire cluster. And so each machine gets a portion of it. And what you do is you call the Blur main controller with a query, and then that query, same one, gets sprayed to the entire cluster. All the results get gathered up, and then you can have a search that's faster because you've spread it over you know, a larger number of machines. And you can actually download Blur. I think we've done it at some of the coding nights. If you want to read where all the mathematical stuff came from, there's a great book, Introduction to Information Retrieval. It's available at the Stanford website for free as a download in multiple formats, PDF, etc. So you can read more detail. That's it. Thanks.